Let me welcome all of you to this lecture and also welcome our speaker, Professor T. Padmanabhan, to the Institute. This is part of the Infosys Science Foundation lecture series, and these lectures are given by recipients of the Infosys Prize or by the jurors who have been involved in making decisions about the award of the Infosys Prize. And this afternoon we are very happy and privileged to have with us Professor T. Padmanabhan from the Inter-University Center for Astronomy and Astrophysics. He's currently Distinguished Professor and Dean at IUCAA in Pune. Professor Padmanabhan is one of India's most distinguished physicists. He obtained his degrees, bachelor's and master's from the University of Kerala and did his PhD from the Tata Institute of Fundamental Research in Mumbai. And he is one of the foremost authorities in the areas of gravitation, cosmology, and has won very wide national and international recognition for his work. He has won in addition to the Infosys Prize, which he received a few years ago, I think he also has received the Al-Khwarizmi Award. He's received awards from the University of Melbourne for his work, and also, of course, the Indian awards, the Shanti Swarup Bhatnagar Prize. He's a fellow of all of India's academies and also the Academy of Sciences of the Developing World. We are indeed privileged to have Professor Padmanabhan with us today, and I'd like to request him to present his lecture on cosmic history and mysteries.
Let me begin by thanking Professor Balram for the kind introduction and ISF for making this lecture possible. So the talk today is titled very loosely as Cosmic History and Mysteries, and this is supposed to be a public lecture, and since the public of Bangalore is very unlikely to be all made of cosmologists, I thought I will start with a very reassuring slide telling you that cosmology is very simple. Okay, so there is nothing to be scared about, and what this little guy out here is doing is one of the two things. He is essentially trying to connect the structure of physical laws as we know today with the structure of the universe as we know today. And you can do this in two different ways. One is you test your laws of physics in the laboratory. I will describe to you how it has been done, and use that to understand the structure of the universe. And we have been remarkably successful in that. We understand the cosmos from a fraction of a billionth of a second to about 14 billion years. That is a fairly long time by any standards, and I think this is good. This is very good that we are doing this, and it is very satisfying. But the really fun part comes not from this, but from the other side. Because cosmology offers you a unique opportunity to test unknown physical laws, laws of physics which are not tested in the laboratory, using the universe as the biggest laboratory. Frankly, what can be bigger than that? And try to figure out what it tells about the structure of physical laws. So here we are going to before 1 billionth of a second, and that is the real fun part about the cosmology, and I'm going to talk mostly about that, not about the sort of known structure, but I have to introduce the known structures and the known part in order to go to that. So let me begin by first talking about the structure of the physical laws, and then connect it up with the structure of the universe, and then go from the known to the unknown. Okay. One way of looking at the structure of physical laws is to think in terms of three fundamental constants, which I am sure all of you are familiar with. The first constant, so I sort of draw a three-dimensional diagram, and this is the Newtonian gravitational constant g, this is the Planck constant h cross, and this is the speed of light. Just for technical reasons, instead of plotting speed of light, I am plotting the inverse of the speed of light. So here is a cube at unit distance from all of them, and you could have chosen units in such a way that they all take the values 1. And you would like to know what kind of physical theories you get when you travel along this cube. Let us first go along any of the axes. If you just go along the Newtonian gravity axis, what you get is the Newtonian mechanics, which is quite powerful. It sort of governs virtually every part of the macro world, quite a lot of cosmos, planetary systems, etc., etc. It is more revolutionary when you move along this direction. If you just switch on the speed of light, keeping the other two at zero values, you end up getting what you would call special theory of relativity. This was Einstein's brainchild in 1905, and it did two things for you. One thing all of you know, so I don't even have to mention, E equals mc square. Mass and energy are one and the same. The other one, it also told you that the space and time are not separate entities but a connected whole called the space-time, and the notion of time is relative. That is, if you start moving, the rate at which your clocks will tick is going to be different from if you do not move. So this was a major thing which special relativity brought in. If instead of going in this direction, you go in the direction of H cross, you end up getting what is known as quantum mechanics. Now, quantum mechanics is a weird part, probably the weirdest part of physics which we know today. This governs the entire micro world. It tells you how small things like atoms and subnuclear particles and molecules and all of chemistry comes from quantum mechanics, so to speak. It also sort of cuts at the roots of an assumption which we normally have in physics. You would have thought that if I throw a ball up, I can measure its position and its speed simultaneously at any given time and then predict its next, where it will be at the next nanosecond. Uncertainty principle tells you that you cannot measure, for example, the position and speed of a particle simultaneously, and various consequences of that is built into this theory. So I said if you go along this direction or this direction, you end up getting gravity, special relativity or quantum mechanics. What if I switch on two things? Suppose I switch on special relativity and also try to incorporate gravity into it. Then you end up getting what is called the general theory of relativity, and that takes special theory of relativity one step further. This is a major paradigm shift, and it tells you that gravity is not a physical force interaction, but it is just a manifestation of curvature of space-time around a massive body. This massive body curves the space-time, and if something rolls down here, you might think that it is an attraction, and that is the way gravity gravity gets interpreted in general theory of relativity. There is also a very elementary law Einstein wrote down. This happens to be actually exact with proper interpretation. It tells you that if you just look at the radius of curvature of this is curved, so I can fit a curve here, circle here and measure the radius of curvature. The radius of curvature and the energy density which is curving the space-time are related by this very elementary relation. So the amount of energy, if there is large amount of energy density, it will curve very sharply. If there is very less energy density, it will not curve so much. It is like bending a metallic wire to different radii. This is totally inevitable that we use this in order to study our expanding universe. By and large, the density decides the radius of curvature, and radius of curvature tells you a time scale, that is the time it takes for light to cross that radius. And in that time scale, the size of the universe doubles. When the universe was very young, 1 second old, it was doubling in its size every second. Now that it is 14 billion years old and a bit tired, it doubles itself only in 14 billion years or so. But it just goes on in the same way, and this is all which you need from general relativity to understand the cosmos. Now, instead of going in this direction, suppose we went in the other direction, we switch on special relativity and quantum mechanics, you end up something very fascinating called quantum field theory. And the most important result from that which we will need is that it tells you that what you thought was nothing, the vacuum, is a region of intense activity. There are fluctuations in the fields, and particles and antiparticles are constantly produced and annihilated in the vacuum. And this is an artist's caricature of what a vacuum fluctuation should look like. It also tells you that for every particle there is an antiparticle. Like for electron, there is an antiparticle called positron. Might sound a bit esoteric, but this is something which if you are unfortunate enough, you may have to go to an hospital and get done. It is called the PET scan, PET. That P in PET stands for positron. So, this is not very esoteric. You are using antiparticles in actual medical diagnostic. And to every particle there exists an antiparticle as a result from quantum field theory. And the entire standard model of particle physics relies on that. So, we have switched on 2 of them at a time. Now, you want to switch on all the 3. I still do not have a picture here, and that should lead you to something known as quantum gravity. This is where you are going to put together the principles of quantum theory and gravity together. This is the unknown final frontier as of today. Unfortunately or fortunately, it is needed in cosmology. If you want to understand the earliest time scales in the cosmology, you need a quantum model of gravity, at least an approximate model. And it is also possible that relics of quantum gravity, which is very impossible to test in laboratory physics in the near future, may be available in cosmology, and I will give you examples of that in late time. So, this is the sort of survey of the structure of the physical laws which we have. Now, let us look at the structure of the universe. That is comparatively easier because you are more familiar with these things. So, what you would normally think of is sun and a planetary system around it. And if you look at a length scale of something like 10 light years, this is what you will see. There is Proxima Centauri, there is Sirius out here, and there is a whole bunch of stars. Go a bit further. Now, this itself is like 1000 light years. Then you see slightly more dramatic structure. You still have stars, and you can, for example, recognize some known stellar systems. There is Betelgeuse somewhere here it is. And if you want to really see the glory, you have to go this far. So, here you are talking about something like 10,000 light years is this length scale, and you see the Milky Way galaxy with its beautiful spiral arms. And this is the unit in which the cosmologists work. Anything smaller than galaxies, we guys do not concern ourselves with. Okay, so, the galaxy to us is like atoms to a condensed physicist, or molecules to a chemist, or something like that. And the universe is made out of galaxies. So, if you take galaxies as the unit, this is Milky Way, and the nearest big galaxy is something called Andromeda galaxy. And there are a huge number of galaxies around it, which is called local group. This is an actual picture, unlike the artist's impression so far, of the Andromeda galaxy, and this is the nearest large galaxy we have. And we have a veritable zoo of galaxies. They come in all sizes, shapes, and patterns, and we understand most of them. And this is a whole bunch of zoo of galaxies which people have photographed. The way they have distributed themselves in the universe is also very fascinating. If you go to a very large scale, as shown here, you find that the galaxies have patterned themselves into some kind of filaments and void regions. There are regions of emptiness and filamentary structures all over the place. So, this is a deep mystery, in fact, and this is confirmed again and again and again by observation. For example, here is a real observation for you. If only you had eyes to see galaxies and disregard the stars in the sky, this is the beautiful sky you will see. This is real photograph. This is taken from some plate measuring devices, and the color coding is also as real as it could get. So, this is the sky you will see. Every tiny speck in it is a galaxy, not a star, and there are over 1 million galaxies in this region. And you can again see patterns in it. I mean, there are archways and there are regions of emptiness, etc., etc. So, the galaxies are distributed like that. If I turn this around and I put it in a 3-dimensional view, here you are sitting at the center, and a radius vector like this is going to take you away and away and away. And this is an angular scale, and you have sort of collapsed the other scale to a pizza size slice, so to speak. Again, you see that the galaxies here, this is false colors. So, these are overdense regions which are patterned here, and underdense regions, and there are voids, etc. So, one of the primary questions you would like to ask as we go along is that how did these structures form? These are not very regular, they are not like a cubic lattice, they are not completely random either, they are correlated. So, where do they come from? That is something which cosmologists has to answer. So, there are 2 questions which we would like to address. One is, how did these structures form? And we also know how much of matter is out there. If I take all the galaxies and I distribute it uniformly, what is the density of matter in the universe? So, let us start with that. So, usually cosmologists measure this using a parameter which is denoted by omega. So, the omega essentially is normalized in such a way that if omega is equal to 1, then the universe will just have enough gravity to prevent it from expanding forever. Okay, it is like throwing a ball with escape velocity. It will just reach infinity with 0 velocity. If omega is greater than 1, the universe will recollapse. If omega is less than 1, it will continue to expand forever. So, this parameter is what you want to measure, and you can measure this essentially by knowing the amount of matter which is out there. So, the first thing you do is to go and get every galaxy which you can see, add them up, divide by the volume and compute how much it is. When you do that, you get a very small number, you get about 5%, 0.05. So, if all the galaxy which you see is what is there in the universe, then the universe will expand forever, and the omega equals 1, that number which has some theoretical significance is not reached. But the question is, are there things in the universe which more than meets your eye? And in fact, it turns out there is, and there is observational evidence for that. So, let me give you one or two examples. So, here is a galaxy with visible matter here. Fortunately for us, nature has provided us with specks of hydrogen clouds all over, which do not emit in visible but emit in radio, and by measuring that you can measure with what speed those things are orbiting this object. Using that, you can plot how much velocity these as a function of this distance from the center. This is like measuring the speed with which a planet is going around the sun and using that to estimate the mass of the sun, which you can do with essentially 9th standard physics. So, you repeat that and you find that what is observed is something like this. What is expected theoretically if all the matter is the visible matter is like this. So, the deficit between these two tells you that there is more matter in the universe or around this galaxy which is dark and is not emitting in the visible band. So, this goes under the name dark matter. Now, there is another dramatic verification of that which is shown here. If you look at it, you see these arc-like structures. You can even imagine yourself that there is some kind of a large arc-like structure, but there is definitely elongation of these. What are these? These are normal non-arc-like galaxies at faraway distance whose light is coming to us through a nearby cluster of galaxies. So, there are lots of galaxies out there and there is a cluster of galaxies here, and you are seeing the light from that coming towards you. And in Einstein's theory, light gets bent by gravitational force and it also gets distorted. This is a gravitational lens. And this gravitational lens distortion depends on the total amount of gravitating matter there. Not just visible matter, all matter that gravitates does not escape this calculation. Using that, you can again estimate how much matter is there. And the bottom line of all these studies is that the dark matter contributes about 25%. And the normal matter you and I are made of is like 5%. So, we are getting there, but it is still 30%. So, if you take these two together, then the normal matter as the universe expands, its density is going to drop like this, and the dark matter will have higher density compared to normal matter because there is at least 5 times more, and that dark matter density will fall like this. Are these the only constituents in the universe? No. There is another very important constituent, and this is the radiation. And there is all kinds of radiation, but something which is of importance to cosmology is something called cosmic microwave background radiation. Basically, the universe behaves as though the entire universe is kept in a microwave oven and the oven's temperature is set to 2.73 Kelvin. So, it is filled with a radiation in all directions with a temperature which corresponds to this. The reason it is in some sense so strong, so to speak, is that if you have an old fashioned TV with an old fashioned antenna and without too much of noise reduction, then the noise you get between two TV stations, 1% of it is coming because your TV is interacting with the early phases of Big Bang. That is what this radiation is all about. So, this radiation falls in density much faster than the other two, As a result of which, at some stage, I mean, dark matter is what dominates, so let us look at that. The black curve and the blue curve joins at some point, crosses at some point. After that, radiation can be ignored as the universe expands, and it is the dark matter which is dominating. What it tells you is that there is a number, a pure number, the density of the universe at the time of equality between radiation and matter, okay, which characterizes our universe. It depends on how much is this and how much is this. This is a pure number, and we believe that high energy physics can tell us what this number is. There are models which can tell you this number, but keep that in mind. Finally, I want to reduce the story of the universe to a story of 3 numbers. So, this is the first of those 3 numbers. Okay, now let me take up the next question. How did these structures form? Well, the easiest way to do that is to make a universe. So, let us make a universe. So, here it is. You start with some small density fluctuations early on in the universe, and you run a computer simulation, and you find that just Newtonian gravity, which we all know, makes structures like the ones which you see. And the final stage, you see the same kind of filaments and dark regions, etc., etc., etc. So, if you give me an early stage with a small perturbations in the density, and then if I switch on the gravity, everything is fine. I can get to my galaxies, etc. And this is done repeatedly, and you can make it agree with observations. But that is good. It is very good that you have a nice computer and you can run this picture. But is this the way the universe actually formed? Can I test this observation? You can, for the simple reason that cosmologists are a very privileged lot who can see the past. The light from any one of you takes a particular amount of time to reach me. So, when I am looking at you, I am looking at you as you were a tiny fraction of a second earlier. When I look at the sun, I see the sun as it was 8 minutes earlier. When I look at further and further regions in the universe, I am seeing the universe as it was earlier and earlier. So, I can directly see how the universe looked like when it was 1,000 times smaller. If I look at that, that is what this radiation is all about. There must be a way of seeing these fluctuations at that time. If these fluctuations existed, I take it and put it into my computer and I make a universe. So, we want to see that. Well, I told you that there was this 2.73 Kelvin radiation. I was lying a little bit. It is not as smooth as it is. There are tiny wiggles. So, there are regions which are hot and regions which are cold. So, the temperature of 2.73 fluctuates between 2 directions in the sky. It fluctuates by a very tiny amount, few parts in a million. But thanks to technology and thanks to the efforts of people who went after it with a single pointedness, we now have a picture like this. This is remarkable actually. And all the things here is a goldmine of information, and I am going to extract it as we go along. And just to show you what technology has done for us, this is the kind of map which we had in 1992 when the first map was made. This is what we had in 2003. This is what we had in 2030. And it's going to only improve. So, this is the kind of resolution increase of this cosmic microwave background radiation. So, now we have very high resolution maps of this, using which you can draw curves like this. I know that most of you will be a non-technical audience, so I don't want to show too many graphs for you, but there is one point I want to make on this. Forget what it is. Essentially, it is a measure of how much the temperature differs at some angle. Like take 0.2 degrees in the sky, take 0.2 degrees off, and you just measure how much the temperature differs at that angle when I average all over the sky. So, at 0.2 degrees, it differs by this much. That is what the graph tells you. But you see that it has some remarkable structure. It has peaks, ups and downs, etc. There is a blue curve which is a theoretical prediction, and the red points are data. So, there is a theory which can exactly reproduce this curve, and the question is what kind of theory is it? What ingredients have gone into reproducing this? So, these are the fluctuations, and now I have pushed the stage one step further. I said if you give me these fluctuations, I will run my simulation and get you the galaxies. But obviously, you will ask where did these fluctuations come from? I have to answer that question. And I also have to make sure that with these fluctuations, I can actually lead to the structures which we see. Well, you can do both. So, let us look at the picture. The answer to where this comes from is essentially the vacuum fluctuations at the very early universe. In the very early universe was quantum mechanical. It had vacuum fluctuations, and these vacuum fluctuations were enhanced by gravity and led to fluctuations like this. And the other answer is exactly the simulation I showed you, and it leads to these structures. So let me look at this part once again. Okay, there are some interesting things to learn there. So here are the vacuum fluctuations in the early universe leading to this, and what do you need for that? It turns out that you need for that something which cosmologists call the inflationary phase in the very early universe. Some of them got jobs in Wall Street because people misunderstood what they were talking about. But this is the term which is used for that. What does the inflationary phase mean in this context? So here is this picture again. This is the energy density of radiation. This is the energy density of dark matter, and this is the total energy density. The inflationary phase, which is what is required in order for this beautiful matching of theory and observation, tells you that somewhere along the line there was a constant energy density phase in the universe at very early moment. This is before that 1 billionth of a second, which I told you about. That is why it is exciting. If it is there, you can explain this. This implies this, so to speak. So you have an inflationary phase of the universe here with constant density. What does constant density mean? Constant density means constant curvature. Constant curvature means constant doubling time. So the universe was doubling at the same rate. It is like your national savings certificate doubling every 7th year or something. It is an accelerated exponential growth in the simplest term. But when density starts dropping, that doesn't happen. It slows down. It doesn't slow down here. It's an accelerated expansion. That means there is one more number here. There is a rho at the inflationary phase, the density at the inflationary state. I originally gave you one number, so I have got you two numbers which describes the universe. We again believe that high energy physics can in principle determine both these numbers. So no problem. There are models which will give you both these numbers. Now let us go to the last part, that it is here and you want to get these structures out of that. This is fine, but here is where a deep mystery came up when people did these studies carefully. To do that, you need to input the nature and amount of matter of different kinds in the universe precisely. And the answer you get, the kind of universe you build, depends on what you input. In order to get the right answer, you need a weird composition for the universe. Your atoms form about 5%. The dark matter I have already told you is 25%, but that is not good enough. The rest of the pie has to be made of about 70% of something which I will call cosmological constant. It is a term in Einstein's equation. That is, you have to modify Einstein's equation by adding a particular term. If you do that, you get this, and this implies this kind of composition. Now, this is for those of you who read popular literature, this is what used to be called dark energy. That brings you Star Trek and Star Wars and Dark Vader and all that. I mean, it is just a term in Einstein's equation. So let us keep it simple. It is just cosmological constant. Every observation we have is consistent with it. So we don't have to get mystical about it. So you have this, and how do we test this again? I told you that if there is something like this is going on, then the cosmological constant, since it is a constant energy density, when it dominates the universe, it will again accelerate the expansion of the universe. So what I need to do is to go and find out whether the universe is accelerating or not. So I told you that we guys are privileged to see the past. If you just keep looking further and further, you are looking at earlier and earlier phases of the universe. So you just want to know whether the rate of expansion of the universe today and the rate of expansion of the universe yesterday was different, and if so, whether the expansion rate is going up or coming down, whether it's accelerating or decelerating. So it's very simple. Well, there's a small catch. If you want to look at things which are further and further away, the light from that will get dimmer and dimmer. So even with the best telescopes, at some stage you reach the limit of your observation. So two things came along. One, again, technology. Hubble Space Telescope broke the technology barrier, and one could make measurements much deeper in space. Second, nature has provided us with some beautiful things called supernovas. These are end stages of some massive stars which just explode off. This is a picture of what is known as the Crab Nebula. This is a large picture of that, which was noticed by Chinese astronomers in 1054. It was also noticed by Red Indian tribes in America. 1054 is plumb in the middle of the height of Chola kingdom in South India. We have no record of that, but it happened on July 4th, so maybe it was a very heavy monsoon that period. Okay, but it is rather unfortunate. We don't have any record of that. Chinese had a record of that. This thing was visible for nearly 6 to 8 months to naked eye. At the peak, it was brighter, 8 times brighter than Venus, and it could be seen through daytime. So this is a beautiful supernova explosion which went off in our own galaxy. But of course, now we can measure far off galaxy things. So if you take all that data, using that to measure how the speed of expansion of the universe changes with the size of the universe, this is what you get. Well, you don't have to be a genius to figure out that it is accelerating. The speed of expansion of the universe is going up here. It was nicely coming down, it turned around and it is accelerating. It has started accelerating when the universe was about 60% its current size. So this data was from various people, but this way of presenting it is done by me and Tirthankar Roy Chaudhary, who is right now at NCRA. This also means that the cosmic energy density sort of comes down. It is from the same data, you can measure the cosmic energy density, and it reaches a plateau. This constant is what I call the cosmological constant. I mean, give or take constant factors, okay, in the definition. So there is a constant energy density from the cosmological constant to which it is going through, and this excess is provided by the matter at this present size. So what is this? Well, as I told you, basically it is a sign, it is a term in Einstein's equation, and it has a peculiar property that it acts as though it is a fluid with negative pressure. So if I fill balloon with gas and then I let the gas do work on the surface of the balloon and expand, as it expands, its temperature and energy will come down because it is doing work and it is expanding it. That is because it has positive pressure. Suppose I fill a balloon with negative pressure gas, then it can push the balloon up, and at the same time it can do the reverse. The energy can go up or even remain constant. Cosmological constant adjusts itself in such a way that as the universe expands, these two things balance and its energy doesn't dilute, while everything else is diluting. So it is some kind of a sleeper agent which gets activated at some stage when everything else has gone down. And it can drive the accelerated expansion of the universe at the present phase. Virtually every theoretical physicist believes that this is the most important puzzle in theoretical physics today. So I want to explain to you why it is a puzzle and what is the puzzle. So let us go back to this picture. In recent times, we had this dark matter going down like this and radiation going down like this, and there was a equality here. But the moment I switch on a cosmological constant, the moment other energy densities drop below this, this is going to dominate. So this is going to turn around here. This is what is happening somewhere around. We are somewhere here. So now we have two more numbers in the recent phase. If you put all of them together, we had one constant density phase here when universe was accelerating. There is another phase now when the universe is accelerating. This is because of cosmological constant, this is because of something else, and there is a phase in which the matter and radiation were equal. So there are three densities, and if I know these three densities, I can write down the dynamical equation governing the evolution of the universe, and I will know everything about it. So every universe you want to create of our kind is modeled by three numbers, and the question is to understand these numbers. So when you try to understand these numbers, the really mysterious one is this cosmological constant, which can also be written in terms of a number which has the dimensions of inverse length square. So you take this number and you multiply with the three constants we started the talk with, g, h and c cubed. Okay? This has the dimensions of square of the length. So this is 1 by centimeter square, this is centimeter square. So the product of these two is a pure number. Now we know all these values. This comes from cosmology. It is one of the most precisely measured objects. You can put them together. So you are essentially bringing in gravity, quantum theory, relativity and the cosmological constant, and you end up getting a number which is extraordinarily tiny. Observations tell you that this number, for those of you who are not mathematically inclined, this number stands for 1 divided by 1 followed by 123 zeros. So, it is like 1 by 10, 1 by 100, 1 by 1000, 1 by 10,000. You go to a number which is 1 followed by 123 zeros and 1 by that. It is an enormously tiny number. Theoretically, we have no clue what this number is. At least this was the situation until a couple of years back. So, this is what most people believe is a very strange thing about the universe. Out of the 3 densities which we have in the universe, 2 of them we have a hope for understanding from high energy physics. Not that we have completely understood it, but we have a basis by which we should be able to figure it out. There is a 3rd number which nobody wanted, but observations thrust upon us, which we have absolutely no idea where it comes from. And it can be written in many equivalent ways. The curvature of the universe today in terms of this object is called Planck Length, and usually it is denoted as LP square. So, the curvature compared to that Planck Length is like this, or the density at the inflation and density at now is of this. Large numbers, either very large numbers or very small numbers, depending on how you look at it. So, many people have tried to attack this problem, and now I am going to talk about my own view on this, and that is summarized here. In case you haven't read this book, you should go and read it. The way people were attacking this was that, look, there is this lambda and it is very small. So, we have to find out what is wrong with lambda, and we have to find out why it is very small and why it is not something reasonable. I think the real problem with lambda is not a problem with lambda, it is a problem with gravity. So, let me try to explain that. This part is a bit technical, but I will try to make it as non-technical as possible. The problem has to do with why is gravity immune to energy shifts. So, what do I mean by that? Normally in physics, suppose you measure the energy of something, say suppose you measure the energy of one particular level of a hydrogen atom, and there is another level, and you measure its energy, and you arrange things in such a way that you think of a free electron at infinity has 0 energy, and then you measure the energies. But suppose I decide to add 20 electron volts to all the energy scales in the hydrogen atom, physics will not change. Physics only cares for energy differences. So, we thought physics only cares for energy differences and not for the absolute energy. So, only the energy differences should matter. The only place where this does not hold true is in gravity. Gravity cares for the absolute value of the energy, not for relative energy differences in the standard Einsteinian picture of gravity, the standard picture which everybody accepts. What it means is that if I shift this level of this energy by an amount either down or up, what I do is going to change the cosmological principle or the way the universe is evolving quite a bit. And it turns out that as the universe was evolving, this 0 point of the energy was changing for reasons which are purely technical, which happens in the matter sector. And the gravity should have taken note of it. We find that it did it, which is very beautiful because no other law of physics worries about the absolute value of the energy. Only gravity was caring about it, but now we have a concrete, at least we thought it was caring about it. Now we have a concrete result that maybe it does not do that either. So, the gravity is actually immune to energy shifts. This cannot be understood in Einstein's theory. The second is, fine, suppose I do that, that is like throwing baby with the bath, because after all the cosmological constant has a numerical value. So, not only that you have to make it immune to shifts in the energy, you also somehow arrange things in a way that that 0 level of energy, when the density went down and there is a plateau, you have to give me that numerical value. So, how can we do that? How can you get this number out of nowhere? It turns out that you can't do it in standard Einstein's theory, but it requires a new paradigm shift. So, this is a paradigm shift which I have been working on for the last decade or so. In the last part of the talk, I want to describe that to you. What it tells you is that gravity could be something which is technically called an emergent phenomena. That sounds like a big word, but it is something which all of you are familiar with it. What is an emergent phenomena? The simplest examples of emergent phenomena is fluid mechanics, flow of water or air, or elasticity. You have a steel bar and you oscillate it and it goes up and down. Okay. What is peculiar about it? The peculiar thing about fluid dynamics, for example, is that it has a life of its own. If an engineer is studying the vibrations of an elastic bar, a steel bar, he doesn't care the atomic physics inside. You tell him some aspects about the Young's modulus and a few stress constants, etc. He will tell you how it is going to vibrate. If he starts asking you what atoms they are made of, he is a very bad engineer. Okay, so the cantilever vibrations, I can write down a theory for elasticity. Same with an aeronautical engineer who is worried about the flow of air across an airplane wing. He doesn't go and do molecular dynamics and how each molecule is colliding with the wing. He can just write down a law for that. These are emergent phenomena. So, these are phenomena at very large scales where you don't care about the microscopic physics, and you can describe them by equations like this, which is an ideal gas equation. You don't need to know what it is made of. And gravity could be a phenomena like this. In this case, the dynamics is reasonably independent of the microstructure, and what the picture which is emerging in the last 10 years work or so by me and other groups is that gravity could be the fluid mechanics of some unknown atoms of space-time. So, let me try to stress that point. If you take an ideal gas law, PV equals RT, chemists use it, they explain it and everything is fine, and somebody comes along, this guy's name was Boltzmann, and he says, no, you guys have got it all wrong, the gas is not a continuum, it is made of discrete particles, and these discrete particles are colliding with the wall, and I can use this picture and explain for you this law. Very good. Then they asked, what are these discrete particles? Have you seen it? Nobody has seen it. So, at that time, nobody knew what the atoms or molecules are. The only thing which we had to go at that time was that if you use that picture, then I can write down this equation which you verify. Today, we haven't seen the atoms of space-time. We have no clue what they are. But you can understand a lot of gravity from this, and we are almost like the 2 centuries back physicists who were trying to understand the structure of matter before the atomic picture of matter became very clear. So, what we need to do is to study gravity the way physicists studied gas dynamics before knowing the structure of matter. The problem is the following. Problem is purely one of technology and observations at this level. When Boltzmann and others did this and found things, very soon it was experimentally obtained. But here what we are talking about, the discreteness scale is very tiny. And I want to explain to you and sort of impress upon you how tiny it is. Here is a picture of the macroscopic scales in the universe in factors of 10. Here I have gone 10, 100, like 10 times that. This is 10 multiplied 20 times, and this is 30. Here I have reached the edge of the universe. Okay. Now, suppose I play the same game in the other direction. I go into smaller and smaller and smaller scales. This is sort of the end of laboratory physics. We haven't probed scales below this scale. That is all we have reached compared to macroscopic scales. And even if you take every theorist on his face value, you can go up to this, because we have some kind of a theoretical framework for what is known as grand unified theories. Okay, you can go up to this. The things which I am talking about at Planck length is still outside. So, you have to go further in the microscopic scales by factors of 10, more than you have gone from your scale to the edge of the universe in order to understand what is going on here. So, direct experimental observation in the laboratory is going to be very difficult. Maybe yes, some clever thing will come up, but it is very difficult. But cosmology can be used, because cosmology directly uses this energy scale. So, cosmology is the laboratory for you to check this out. So, I have to give a little bit more details about this emergent gravity paradigm, what it does. So, it looks at gravity as an emergent phenomena, and what it shows is that you can actually write down the equations governing the gravity, like the ideal gas equation I told you, as laws for gas dynamics or fluid dynamics. You can actually do a translation table and write it down. And the added bonus is that it doesn't lead exactly to Einstein's theory. There is a small departure. In this particular model, gravity is immune to energy shifts. And it comes because of a technical reason with null vectors and whatnot, which I won't go in, but just believe me, it solves the problem of energy shifts. It puts gravity at base with all other known physical theories. It doesn't care about the absolute value of the energy, it only cares about the relative value. But when you apply it to the entire cosmos, something new emerges. You end up measuring a quantity which is very similar to what chemists would have called the Avogadro number. You see, even before we knew what molecules are made of, we were counting how many of them are there. Okay? And that was contained in the gas constant R. And if only we have been measuring temperature in energy units, we would have got N, which is 10 to the 24 molecules which are there in a particular STP. So you could similarly measure the Avogadro number of space-time. I don't know what the atoms of space-time are, but I can count them. And I find that every surface has this much of atoms of space-time. So 1 square centimeter of the surface will have about 10 to the power 66 atoms of space-time, because that is essentially the inverse of this LP square. And then if you take a surface and you have a bulk degrees of freedom and the surface degrees of freedom, the dynamics arises only when these two are not equal. This is a very beautiful principle, so I want to illustrate that in some simple way. So here is a surface. This is just a 3-dimensional surface drawn in 2-dimensional space. And on the surface you have an area, and to that area you associate certain degrees of freedom, the number of atoms of space-time. There are also some kind of degrees of freedom living inside, which is n bulk. Now we want to know whether the geometry in this region, the curvature in this region, so to speak, which Einstein would be interested in, whether it is changing or not changing. You can write down a very simple equation, which happens to be equivalent to Einstein's equation, which tells you that this dynamical evolution is essentially proportional to this object. So if the n bulk is equal to n surface, the whole thing is static, nothing happens. You get a static geometry which is not changing in time, and the curvature radius does not change in time. And if they are different, it drives the expansion. In the case of universe, it is just the curvature radius which is changing. Now this is the way emergent gravity would look at normal gravity. These equations are equivalent to Einstein's equation, except for that energy shift which I told you about, but they contain a completely different perspective of gravity and space-time. In cosmology, it leads to a very new insight. I told you that there are these 3 densities. You find that when you work it out, in this phase and in this phase, the n surface is equal to n bulk. So it is in some kind of an equilibrium, and in between it is not, and that is why it is being driven from here to here. This is the picture which emerges when you apply the emergent gravity paradigm to understand the cosmological evolution. So as I told you, it sort of tackles the 2 problems which I raised. The first problem I have explained. I have said that there is an emergence in this particular way of looking at things. You work with degrees of freedom and how these degrees of freedom interact with each other, and why the difference in these atoms of space-time distributed on the surface and distributed in the bulk drives the evolution. That has a consequence that I have not demonstrated it because it requires fairly detailed technical knowledge. That has the consequence that shifting the energy density does not affect the gravitational interaction. That part is fine. But I still have to tell you where the number came from. I told you that ultimately I have to explain to you where 10 to the minus 123 came from, or rather what is the connection between these 3 densities. This was hanging loose for several years, and we finally cracked it last year. I can now write down a formula. When you use this theory and take it to its logical conclusion, it turns out that there is an extra conserved quantity in the universe which people did not suspect, which counts the number of degrees of freedom which can be naturally defined at Planck scales. So it uses in a notional way Planck scale physics, just like 17th century physicists or chemists would have used the notion of molecules without saying it. If you do that, you get a remarkable formula. This formula connects the cosmological constant, the three densities it essentially connects. It tells you if you give me these two densities, which I know high energy physics will tell me one of these days, and we already know roughly what they are. If you give me those densities, then I can compute this density. And those of you who don't want mathematics can just ignore this. Just believe that there is a connection between these three densities which come from that. But those of you who know mathematics will immediately see that a number like this is extremely tiny. And here is where your 10 to the minus 123 essentially comes. This is not 10 to the minus 123, but when you plug everything in, that is where the origin of that comes. This theory actually makes a prediction as well. So it is a testable theory. Okay. So this is purely for those of you who know a little bit more than the average audience. What it tells you is that observationally, see, theoretically this is the dark horse which we want to understand. But observationally this is measured very well. We know what it is. And we also know what this is, but inflation scale is not known. So you can reverse this and it tells you that the inflation scale is very narrowly constrained between two numbers. Just look at 1.2 and 1.1. So if the inflation, it turns out there are some minor caveats by which it can go up by a factor of 5 max. So if observationally somebody comes up and tells you inflation took place at a scale which is outside this theory is dead, this model is dead. So this theory makes a very strong prediction that the inflationary scale is narrowly confined within a factor of 5, which has never been done before. And that tells you that there is a way of understanding the very small scales in the universe, less than 1 billionth of a second, and what is happening today after 14 billion years in a very natural way. And that is what this formula is all about. This is 14 billion years away physics, and this is physics at less than 1 billionth of a second. And this is somewhere in between. And there is a connection which emerges between these three. So let me just summarize. So the first thing I told you is that we do understand the evolution of the universe from a tiny fraction of the second to 14 billion years. And as I said, it is a very satisfying thing, and if you decide to just work on this phase of the universe, you are doing fine. But as I said, real fun things are asking for earlier phases than that. And there we believe, and we have enough evidence to believe, that the vacuum fluctuations generated during the very early inflationary phase of the universe can act as the seeds for the structures which we see today. That is beautiful, because that sort of puts one complete theme right throughout. You have vacuum fluctuation, it generates the fluctuation, we see it in the cosmic microwave background radiation, you run it forward and you get the structures today. We understand that. If you want to do this completely correctly and get the observed distribution of galaxies in the sky, you need one more thing. You need something which I have called the cosmological constant, which has to contribute about 71% to the energy density today, and it has to accelerate the universe, because observations tell you that it is accelerating, and from that, working backwards, we can calculate what this number is. This, as I told you, is the major question, and it requires yet another paradigm shift. And what I would suggest is that this emergent gravity paradigm explains not only the value of the cosmological constant, and also the immunity of gravity to the energy shifts. And as a result of which, we hopefully will have a complete picture of the cosmos right from a very fraction of the second all the way to today. Thank you very much.
One question, one clarification. First clarification that the length of this atoms of space-time, is it bounded by the Planck's length, or could it be smaller? So during the inflation stage, it was in sort of an equilibrium where the rate was 0. I mean, it was not changing, and it's coming back today like that. So what caused it to deviate from the equilibrium?
Okay, there are two reasons for that. One is that, as I said, since it's a public lecture, I sort of simplified things a bit. The inflationary energy density is actually slightly dropping. It is not strictly constant, so this statement is slightly approximate. Similarly, here also this is not strictly constant because there is matter today. Cosmological constant is constant, but there is a tiny amount of matter there, but it is being exponentially diluted at both the things. What really caused this to do is the dynamics of, let us say, the scalar field which was driving the inflation. Another way of thinking about this, which I like, which is mathematically equivalent, is that this phase is unstable while this phase is stable, that you can show. Yeah. So it is, I would really love to think of it as an energy level diagram. So there is an excited state of the universe and there is a ground state of the universe. It is making a transition. We guys are caught in the middle and we think we are very important. Just a transient phase.
Yes, that the rho inflation and the rho lambda.
Yeah.
Both are of same nature, as in they both have negative pressure.
Yes.
So they both should have the same source or.
No, they don't. And that is a mystery which we address to some extent, others don't. So the question which you are asking, I can paraphrase. How is it that the universe is constructed among all other weirdness, this weirdness, that it went through two accelerated phases of expansion, right? There was an accelerated phase of expansion here, there is another accelerated phase of expansion here, and it has negative pressure, this has negative pressure, this has an inflationary energy density, this has an energy density, and they are not connected in any way. What we show is that there is a hidden conserved quantity in this phase, and this phase, a pure number, which in some suitable normalization becomes 4 pi. Okay? And it is this number which gives us this formula. That is the connection between rho lambda and rho inflation.
Yes, is it? So this graph again?
This one?
No, the end surface.
Yeah.
So you're saying that these two have end surface equal to end bulk. So what is the difference then between?
Yeah. So that is what I was trying to explain. The n surface equals n bulk is a simple way of characterizing it, like saying that something is in equilibrium. But then you can ask, what are the constituents? What is in equilibrium, right? So here, what is in equilibrium is some particular kind of high energy scalar field yet with matter, while here it is just plain and simple one term, one cosmological constant term in Einstein's equation with the rest of the normal matter and radiation. So the internal dynamics is completely different. So this is exactly like using ideal gas equation. Suppose I have an ideal gas law for helium and I have ideal gas law for argon. Ideal gas law is ideal gas law, but argon is very different from helium, and they both can be in equilibrium at a given temperature and density and pressure. That is what is happening. That is an analogy. Yeah.
I see. So some set of degrees of freedom.
Absolutely. Those degrees of freedom are completely different, but the numbers match.
Is there a conservation of those atoms also involved?
Yes. The hidden conserved quantity which I talked about, but I didn't go into details, it involves, as I said, it involves some technical calculation, but ultimately it is a measure of the total number of atoms of space-time which is going through. It is a count of the degrees of freedom at a particular surface. So at a very primordial stage, the minimum surface you can have is a surface with a radius equal to Planck length, and that surface will have a particular number, and that number is just 4 pi because it is 4 pi r square upon r square, and that number is propagated throughout the universe, and using that you can get this relation. Yeah, that is correct.
Okay, there are two quick questions there. Yes.
So as this theory predicts that gravity is immune to the energy shift, so is there any experimental verification, or can we experimentally prove that whether the gravity is immune to energy?
Unfortunately not, because this energy shift has to be global, because gravity cares for all that is out there. So how do I operationally shift the energy in one place? It is not like hiking up the voltage of a capacitor plate and saying V has gone to V plus V naught. You have to hike up the energy shift everywhere. Therefore, only cosmology can answer that question. However, we do know if our standard model of particle physics is correct, and the Higgs boson has told us that we are on the right track, when the universe went through what is known as the electroweak phase transition, this energy did shift by a very large amount from a broken symmetry phase to a symmetry restored phase. But we don't see any signs of it in the cosmic evolution. Nothing peculiar seems to have happened. So we do know that there are times where if the standard model of high energy physics is correct, the ground state energies has shifted by a very large amount, and the gravity seems to be immune to that. I would like to argue that that is an experimental proof, but it is not the kind of experimental proof you have in mind. It is not a lab testable statement. Yeah, I don't know any way of doing it.
I have a two-part question. Do we know what was the time frame of the shift from the inflationary to the lower energy?
You mean from here to here? Oh yes, we know that very precisely.
Okay.
Yeah.
I would like to know, I mean, how far back did the
Well,
start to?
I don't think in terms of seconds, I think in terms of energies. So the energy scale here is like 10 to the 15 GeV, 10 to the 15, 10 to the 16 GeV, and the energy scale to here is like today's energy scale. It's very tiny. It is like 2.73 Kelvin's energy scale. So from that you can compute it out. Roughly, if I quote from memory, universe expanded by a factor 10 to the 28 between these two.
And presently we are in the lower.
That's correct. Presently we are somewhere here.
Has the solar system ever encountered a transitional region?
This transition, you mean whether the solar system was around at this time? Well, the solar system was around somewhere here. Okay, so solar system in the scheme of things is very young. Okay, yeah.
Okay, perhaps on that note, let's sing. I would like to thank Professor Padmanabhan for a very thought-provoking lecture, the Infosys Science Foundation for sponsoring it, and all of you for being here. Thank you.